What are you doing?
Like 8 of us that are here.
Yeah. I count 11, not including me. I'm going to chalk this one up to just being exhausted and hope that we have more people showing up next week. Otherwise, I'm going to start taking attendance every single day, and that's just annoying. 12 people. So today, I really want to get into a discussion of magnetism. And first, I kind of want to talk about what it is. So I'm going to put a symbol in there, and I can't type symbols, so I have to write it with a pen. So magnetic fields are symbolized with the capital B, and they are a vector. Actually, technically, they're a pseudovector, but the difference between regular vectors and pseudovectors is a little technical for our class. But they are a quantity. They have a direction, and they have a strength. And the strength is measured in Teslas, capital T's. And there's a couple of things you could say about what magnetic fields are. They are they're kind of, in a sense, a virtual wind. So when we trace out magnetic field lines, there's this stuff called magnetic flux, which is actually built out of photons, similar to what light is built out of. And those photons follow the magnetic field lines. And the magnetic field itself is kind of the net effect of all of those bits of magnetic flux. One weird thing about magnetism, and this is one of the things we stress in this week's lab, at least in the pre-lab, is that magnetic fields always circulate. There's no origin or destination of the magnetic field. This is a little different from electric fields, where electric fields point away from positive charges. So you could think of positive charges as an origin of electric fields. And electric fields point toward negative charges, so you could think of negative charges as a destination of electric fields. But magnetic fields always circulate. There is no origin or destination. They always form loops. If you follow the magnetic field arrow and then see where the next magnetic field arrow goes and then the next magnetic field arrow from there, eventually you'll find yourself back where you started. Today, I mostly want to talk about what creates magnetic fields and how to calculate how much magnetism is created by certain things. But we do want to justify it a little bit. So how do we know that magnetic fields exist? One thing that happens because of magnetic fields is charged particles get deflected. So that means that if they're moving one direction and they hit a magnetic field, they'll suddenly be moving a different direction. And the way we deflect moving objects is with force. So magnetic fields create forces. And another thing that happens with magnetic fields, and this is what we did in lab this week, is magnetic fields make compass needles point in the direction of the field. Now, we use this outdoors to tell us which way's north if we don't have like GPS navigation available. In fact, even your cell phone uses the magnetic field of Earth to help it tell which way is north, because GPS only tells the phone where it is. It doesn't tell the phone which direction it's facing. Now, if you're driving down the road, the phone says, oh, the top of the phone is facing in the direction of the velocity, because it knows where it was, it knows where it is, and it can figure out what direction the velocity is. So it can figure out a velocity-based orientation, and then it can orient your map so that you can see what's in front of you on the map. But if you're stationary, then it has no idea which way is north except by Earth's magnetic field. So that's what it actually uses. So it's not just big old-fashioned compass needles that do this. There's a little digital magnetic compass in your phone that does this too. In fact, you could probably get a magnetic compass app and basically see the exact same thing. Now, the way you change something's orientation is with torque. Torque is a force that instead of tending to push something in a direction, it tends to twist something. And we'll be able to, next week, calculate the amount of torque on different things. Another thing that we can use to detect magnetism is its ability to generate electricity. In this week's lab, you had this wonderful magnetic field sensor, which was basically a plastic stick. Inside that plastic stick is a little coil of wire, and when a magnetic field is present, that coil of wire has a special voltage applied to it, and the magnetic field affects the current in that wire. So by putting that little coil of wire into the magnetic field, the sensor can tell whether or not there's a magnetic field there and how strong it is. And then that's sent back to the capstone. Well, it's sent back to the Pasco Universal Interface, which sends it to Capstone, which displays a result on your screen. So it's the magnetic field's ability to generate electricity in that case, which is used to measure the magnetic field. And this is called induced voltage. And we use magnetism to generate the voltage that runs through the wires in our houses and powers all of our devices. So without magnetism, we would not have an electric system in our world. And another cool thing that magnetic fields do is magnetic fields form electromagnetic waves. And that's really important because light is one of the kinds of electromagnetic waves, visible light, and without visible light, we wouldn't be able to see. Radio waves are a form of electromagnetic waves, and we use radio waves to communicate all the time. That's how most of us communicate with the internet. Is the first step is radio waves to some base station somewhere, whether it's a Wi-Fi hotspot right there, the little blue light on the ceiling, or if it's a cell phone tower a quarter mile away. Either way, radio waves are used to communicate between your device and a base station. So all of those are evidence of magnetic fields. Now, before we get into the details of all of those things, or any of those things, I want to talk about what creates magnetic fields. And there are basically only two things in the universe that can create magnetic fields. Either moving charges can create magnetic fields, which is basically either electric current or spinning charges. And electrons are charges, and electrons do spin. So electrons generate a little bit of magnetism all by themselves. Just their existence generates a little magnetism. And the other thing that can generate magnetic fields is fluctuating electric fields. Now, if you just have a stationary charge with its static electric field, that won't generate magnetism. It takes a fluctuating electric field, an electric field that is growing or shrinking, to generate some magnetism. And we probably won't get into the details of that at all. It's very complicated math that involves calculus 3 concepts and differential equations and stuff like that. But the idea that fluctuating electric fields generate magnetism is what allows electromagnetic waves to form. And I'll describe that process probably a couple of times because I think it's really interesting. So every time I get a chance, I like to say that electric fields generate magnetic fields and magnetic fields generate electric fields, and then they get together and go off as light. So the first magnetic field that we encountered historically is Earth's magnetic field. So I'm going to attempt, I have not done this in OneNote yet, but I'm going to attempt to draw Earth. Okay, so that's a good start. Now I'm going to add continents as best I can. Okay, that's about as good as I can do. That represents Earth. I'm not even going to try to draw Europe. I'll just make it worse. There's something resembling North and South America there, sort of. Now, the magnetic field of Earth points north. So wherever you are on the globe, the magnetic field points north. There's only one problem with that idea. Magnetic fields are supposed to form loops. So what actually happens is these magnetic fields go up to a point up here, approximately, and then they go through the center of Earth and pop out the other side. So that's a rough model of what the overall magnetic field of Earth is like. It points north on the outside, but then on the inside, it actually points back south again. Yeah. So away from the poles, on the surface, B points north. At the poles, the magnetic field points inward or outwards. Now we have special words that refer to inward with respect to the Earth and outward with respect to the Earth. They're very common words, up and down. So at the South Pole, the magnetic field points up, because if you're standing on the South Pole, your feet are on the Earth, and your head is like toward the bottom of the drawing, and the magnetic field points from your feet toward your head, that's up. And then at the North Pole, the magnetic field points down. And you could call those inward or outwards. And roughly the strength of the magnetic field, it varies by like a factor of 2, plus and minus. But a good round number is 50 microteslas, which is 0.00005 teslas. Yeah. Now, your magnetic field sensor in the lab basically will measure 4 digits after the decimal point. So your magnetic field sensor that you use in the lab, the Pasco magnetic field sensor, by default won't quite measure the Earth's magnetic field. It's just short of being able to do it. But that's going to be a kind of a benchmark for what a strong magnetic field is for me. If you could generate a magnetic field that's stronger than this, then a compass in the area will see your magnetic field instead of seeing the Earth's magnetic field. And basically, you'd mess up a compass. That doesn't mean you'd mess up the GPS signal. That part of navigation would still work. But a plain magnetic compass would get confused if we created a magnetic field that was stronger than this. Now, I'm going to come back to this drawing, but I want to go to another type of straightforward magnetic source, and that is a bar magnet. Otherwise known as a permanent magnet. So a nice straightforward drawing would be just a nice rectangle. And I'll put a label on it that says N. And in lab this week, you should have seen that the magnetic field was pointing away from the north. And the other end would have magnetic field pointing inward. We call the other end a south. So we say the magnetic field points away from the north and toward the south. And then if you put compasses at other places around the bar magnet, you should have seen something that looks like this. Off the page, back on. So this one was a nice little loop. This one was a slightly bigger loop. And this one was a big bulbous loop. There's actually a really nice PhET demonstration of magnetism. PhET physics. Electricity and magnetism. They don't have the HTML5 version. That means I can't necessarily do it. They have a Faraday's law one. I'll have to search through that and find a good demonstration that I can run on the screen. But it would basically show this just with better graphics. So if you have a magnetic object, it generates magnetic fields. And if you go and measure the magnetic field of your magnetic object, anywhere where you find the magnetic field pointing outward, that's a north end. And anywhere you feel you detect the magnetic field pointing inward, that's the south end. And we call this the north end of the magnet because if you hang the entire thing from a string from the center of mass, so it can float around and point any direction at once, the north end will point north, which I think is that way in this classroom. That's where the water is, the closest water, the Corpus Christi Bay. So what does that mean for the Earth? How many eyes? Which part of Earth had the magnetic field pointing outwards? It was actually the south end of Earth. So my conclusion that I like to draw from that line of reasoning is that Earth is sort of an upside down magnet. That the geographic north of Earth is a physics south, and the geographic south of Earth is a physics north. And you could kind of justify that by thinking about having two Earths. If you had two Earths, you'd have, I'll put the geographic north in blue and the magnetic north and south in red. So this is the north and south poles from magnetism's point of view. If I put another Earth next to it, the magnetic north would be attracted to the other magnetic south, because with bar magnets, opposites attract. So this would form north like that and south like that, and you'd end up with loops of magnetism that go out one magnet and in the other. Whoops, that's not what I meant to write. So So the south pole of the second Earth is north-seeking from the perspective of like putting it near the original planet. And that's what we use to define what a north magnetic end of a bar magnet is when you let it do what it wants, which end points north. So that's a little bit of weirdness.
If you had two Earths like that, like normally if you just have one, it comes back around over the Earth and goes back in.
Yeah.
But if you have two, would those loops just go like that, so you wouldn't have a...
There'd still be some magnetism that would leave the north and go around the other side and come in the south. But a lot of the magnetism that leaves the one north would get sucked in by the other south. And a lot of the magnetism that gets shoved out by this north would get sucked in by that south. So imagine imagine using a vacuum cleaner. So you have the hose of a vacuum cleaner, and then you have one of those cans of spray air. If you blow dust off the table and have the vacuum nearby, it'll suck up a lot of the dust that you blow up off the table, but some of the dust will still scatter all over the place. That's kind of what happens to the magnetic fields. The north end is blowing out magnetic flux, and the arrows represent the direction of flow of this magnetic flux. The south ends are sucking in magnetic flux. And since these are two equivalent Earths, this north is emitting the same amount of flux as this south is absorbing. It's just, it doesn't all connect. Some of it's going to go around the other side. Magnetism has this tendency to spread out all over the place. It won't all get focused in exactly that way.
Kind of a sidetrack question.
Sure.
How did the Earth get a magnetic field?
Why does the Earth have a magnetic field?
How did it get?
Yeah. Well, they're kind of the same question. How did the Earth get a magnetic field, or why does the Earth have one in the first place? Earth is spinning, and Earth is filled with conductive fluid. And as it turns out, when you have a spinning object, the middle is moving slower than the outside. And when you have a fluid where you have one part that's moving fast and another part that's moving slow, that is a shear stress on the fluid. And the viscosity of the fluid determines forces that happen in the fluid because of that. So if you put a really light oil on a table and move your hand around, you would feel a certain amount of resistance to the motion of your hand back and forth. But if you put a thick syrup on the table and move your hand back and forth across it, you'd feel more resistance to that. And that resistance is because of the fluid touching your hand, moving with your hand, the fluid touching the table, being stationary with the table. That's fluid being moving with different velocities right next to each other. And because the Earth is a spinning fluid, it has to do that. As it turns out, because it's a conductor, the electrons are allowed to move around wherever they want, just like they're in wires. They have a different viscosity than the atoms. So that means the electrons are stirred around differently than the positive charges. And when you have positive and negative charges moving with different velocities, that's electric current. And then that electric current is what's making the magnetic field. That's the best explanation I have. That's the one I feel like it's true. Unfortunately, that doesn't explain how Earth can have a magnetic field that points different directions at different points in geologic history. So they got me on that part. There is a physics experiment that somebody's doing where they have a giant ball of, I think it's gallium, but it might be mercury, basically a conductive liquid metal. And they spin it and measure the magnetism that they're generating just by spinning the metal. So they're not zapping it with current. They're not hitting it with a magnetic field. They're doing their best to cancel out Earth's magnetic field. It's a big shielded room. And just this spinning ball of liquid metal is generating magnetism. So it is the idea of spinning a conductive liquid that does it.
And they feel the flips, right? Every 1,000 years or so.
I've heard that.
Yeah.
It's not a sudden thing. There are lots of eddy currents inside Earth because there's hot regions. The core is very hot. The mantle has some radioactive material that generates heat, and that's not uniformly distributed. So there's hot spots and cold spots. There's a hot spot under Hawaii. That's why there's a volcano there. So all of these things are moving conductive liquids around. And anytime you have moving conductive liquids, the electrons and the atoms themselves are going to behave slightly differently, and that can generate magnetism. I don't know that the Earth's magnetic field flipping means that it has to go from positive to 0 to negative, because it's big. It could go from positive to 0 to negative at one place and not at another place. But it's also a vector. So the magnetic field could go from that way to that way to that way without ever touching 0. So just because Earth's magnetic field may, in the next 20 or 100,000 years, flip directions, that doesn't mean that it's going to have a 0 at some point. Having 0 magnetic field would actually be really bad for us, because there are charged particles coming in from the sun. And one of the things that magnetism does is deflecting charged particles. And that's good, because if these charged particles hit us, it would kill us. So we don't want that. So we like Earth's magnetic field. We would like it to stay. Now, one of the things that we like to be able to do in introductory physics classes to calculate things. Bar magnets on the Earth don't really give us much of a chance to calculate things. But there are some magnetic sources that can give us a chance to do some calculations. For instance, a wire can create a magnetic field. So we're going to have a long, straight wire. And I think I did this drawing on Monday. We're going to put some current in here. And it's going to create some magnetism like that. B. And since the magnetic field is a vector, we should be able to figure out its strength or magnitude and its direction. So let's do the magnitude first. So the magnitude is a nice straightforward formula. B is equal to mu naught, that's a universal constant, times the amount of current, I, over 2 pi times R. And in this, mu naught is equal to 4 pi times 10 to the minus 7th Tesla times meters per ampere. You actually have to put a multiplication dot in between the Teslas and the amperes. Otherwise, I'm sorry, in between the Teslas and the meters. Otherwise, it looks like terameters. And tera is an SI prefix. It means a trillion. So we don't mean a trillion meters, we mean a Tesla meter. And you can't solve that by reversing them, which is what we do with Newton meters, because then it would look like milliteslas, and milliteslas are a perfectly legitimate unit also. So you're left with separating them with a multiplication dot or a times symbol, or by putting them both in parentheses or something like that. And R is the distance from the center of the wire to the place where we're finding the magnetic field. So this formula says that the magnetic field due to a wire is stronger when you're closer to the wire, and it gets weaker as you get further away. It's a pure inverse proportionality. So, do I have a sample calculation? I do. So, as an example, we could have I is equal to 20 amperes, and R is equal to 2.0 centimeters. So then we could calculate this B. I'm going to leave room for my fraction and see if you can calculate this. It should come out to 2 times 10 to the minus 4th Teslas. mu naught times I divided by big parentheses 2 pi r. So this should be 4 pi times 10 to the minus 7th times 20 over 2 pi times 0.02. That should be what you did. And I think it works out. Now remember that 1 microtesla is 10 to the minus 6 teslas. At the top of the equation sheet, there's a line that has all the SI prefixes that we find important. One of them's micro. Micro is 10 to the minus 6. So that means that 1 microtesla over 10 to the 6 is 1 Tesla. So this B is 2 times 10 to the minus 4th over 10 to the minus 6 microteslas. Which should be 200 microteslas. So this is the magnetic field due to a fairly sizable current. We don't normally encounter currents quite that strong. Most of our household electricity doesn't have currents quite that strong. Maybe a washing machine or a dryer, something that uses a lot of electricity might be that strong. And that would completely swamp out Earth's magnetic field, at least if you're at that distance. You could go 4 times less, and then you'd be at the strength of Earth's magnetic field. So you could go 4 times further away, to 8 centimeters. So if you're within a circle of diameter 16 centimeters near that wire, a compass just isn't going to work right. It's going to work weird. Now, I want to do the direction. So to find the direction of a magnetic field due to a long straight wire, we have to apply something called a right-hand rule. And there are a couple different versions of the right-hand rule depending on what situation you're in. This one, I think, has one of the more straightforward versions of the right-hand rule. There's basically 2 configurations for a right-hand rule, the way I teach it. One is you curl your fingers and stick your thumb out. And then your fingers are forming a circle, and your thumb is forming a straight line. So you take your thumb and place it along the current. So we had a current that was a blue line like that. So you place your thumb along the current. And then the second part is you wrap your fingers around the current, and your fingers are showing you B, the magnetic field. So the magnetic field due to this current is going up the back, out, and down the front. That's the direction of the magnetic field. So up the back, out, and down the front. And usually when I draw this, I draw a break in my circle, which represents the magnetic field going in behind the wire. So that's one way to try to draw three-dimensional magnetic fields. I spent some time talking about words that we use for three-dimensional directions on Monday. We need ways to draw them also. Now there's a whole bunch of points up here that are all above the wire in our drawing. And in all of those points, our fingers would be pointing out of the page at all of those points. So another way to draw this magnetic field would be to represent a magnetic field pointing out of the page, everywhere above the wire. And we have a symbol for that. The symbol for out of the page is dots. So if we put dots all over the place, that means wherever we look, the magnetic field is pointing outwards in that part of the drawing. And I'm using a special symbol here. If you write a thing that's a vector, normally you put an arrow on top of your vector symbol. If instead of an arrow, you put a little caret or a hat on top of it, mathematicians like to call it a hat, that means just the direction of that vector, regardless of the strength of the vector. So at all these points up here, the magnetic field is pointing outwards. And then if we think about the points below that wire, that magnetic field would be curled down the front and pointing into the page, into the screen. So that we have a symbol for as well. That's symbolized by X's. Now notice that I have more X's when I'm close to the wire and fewer X's as I get further away. That's because the magnetic field is stronger when you're close and gets weaker as you get further away. So the way you pack them in gives you hints about how strong the magnetism is. It's not really a proportional thing. It's not perfect, but it gives a sense of how strong things are. So down here, B hat is equal to inward. Now there's a nice mnemonic to remember whether the dots are X's or out or in. And the mnemonic is to think of an arrow, like bow and arrow or dart. If you're seeing the dot, that's the pointy end that's facing towards you. And if you're seeing the X's, that's the fletching that makes the arrow go in a straight line. So you're seeing the feathers pointing, because you're seeing the back end of the arrow, it's pointing away from you. That's the mnemonic to remember which is which. I don't know if that's what the mathematicians were thinking when they came up with that notation, but it's the one that we teach American students now. So that is a representation of the direction of the magnetic field due to that particular current. Now, if we make the current point upward, then that just changes where the dots and X's go. And you could, in a sense, just take this entire drawing and just rotate it sideways, which I don't think I can do in one note, so I'm not even going to try. But you can also just imagine putting your thumb in the direction of an upward current, I, and then the dots would be out of the page if you're left of the wire. So dot, 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 and the X's would be into the page to the right of the wire. What if we were trying to calculate the magnetic field of two wires that are near each other? So we could have two wires. Let's make them point opposite directions. I1 and I2. And here, if I try to draw everything all at once, it gets very confusing. So what I'm going to try to draw first is B1, the magnetic field due to wire 1. So due to wire 1, we lay our thumb along I1, the first current, and our fingers point out of the page above the wire into the page below the wire. So we're going to have dot, 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 X, 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 X. So that's all a representation of the magnetic field due to wire 1, ignoring wire 2. And now let's do a representation of B2. B2. So then we lay our thumb along B2, or along the second current. And we find that above the second current, our fingers are pointing into the page. So for B2, we have all the X's due to I2, or yes. And below it, we have all the dots. So what does B total look like? So I'm going to use ABC to represent region A up above wire 1, region B in between, and region C below wire 2. So BA would have a positive or a negative contribution from B1. Would you call it in or out? Due to B1. I call that out. I think that's positive. Usually we call that the positive Z direction. So in region A, we'd have a plus B1, but then when we go to figure out how much contribution we get from current 2, that'd be the X's, those are inward, those are the negative ones. So then it'd be minus B2. So that would be mu naught I1 over 2 pi R1 minus mu naught I2 over 2 pi R2. So you'd have to pick a point up here, find your distance from current 1, that's R1. Find your distance from current 2, which is a little longer, and that's R2. And then you can throw that together and do some calculations and find the total magnetic field. So let's look at region B. That is a negative B1 because it's into the page, and also a negative B2 because it's into the page. So there we have a place where both contributions due to both wires are into the page, which means we'd have stronger magnetism because we have more contributions to the overall magnetism. And then in region C, B in region C is a negative B1 plus B2. Because B1 is into the page here, B2 is out of the page. Like that, yeah, out. And they would tend to cancel each other out. So we can kind of summarize this. Describing this situation as two currents flowing in opposite directions. And in between the two wires, the magnetic field is amplified. It's a little bit stronger than either one by themselves. Fortunately, when we have two currents near each other, there's not much space in between them. And the magnetic field outside them is actually a little bit reduced. As it turns out, almost all of our wiring systems involve two wires, one carrying current one direction, one carrying current the other direction. So your cell phone charger wire has inside it a red wire carrying current one way and a black wire carrying current the other way. So this is two nearby wires carrying currents in opposite directions. And that means that outside the wire, as in outside the plastic, the magnetic field is actually fairly reduced. And it doesn't cause much magnetic interference with the rest of the world. And our lamp cords and computer power cords, and even our overall electric system are kind of like that. Now, for our overall electric system, there tend to be 3 wires on top of the power lines, and they're kind of balanced out in a weird way. It's called 3-phase power, but it still overall has the net current going one way is equal to the net current going the other way, so the magnetism basically gets canceled out. Now, one thing to remember about this example is we're thinking of both of these wires as sources of magnetism. So we said wire 1 is where it is. It has its current going the one way. Wire 2 has its current going the other way. They're each generating magnetic field, and we either add or subtract their magnetic fields to determine the total magnetic field. We're not saying what force wire 1 feels or what force wire 2 feels. We're just saying that they generate magnetism. On Monday, we'll talk about what force they would feel due to each other, which is a little bit different. Now, of course, sometimes we like to ask questions like, if you have 2 wires near each other, where could the magnetic field possibly be 0? And in order to have a total magnetic field 0, you have to find a place where the 2 magnetic fields cancel and they have equal magnitudes. The 2 contributions have to be equal and opposite. So I'll let you work on a homework question that has that before I try to give away the methods for how to deal with that. The next homework assignment, I'm going to get that posted as soon as I can so that you have something to work on, because I know you hate not having any physics to do. So I'll try to fix that as soon as I can. So the most important source of magnetic fields is magnetic coils. And magnetic coils are based off that idea that if you have current that goes one way above you and the other way below you, that the magnetism gets amplified. So what we're going to do is we're going to have a current that comes out of a battery and then goes around and around and around and around, and eventually the wire's got to come back out again. So in this region here, we basically have wires that go around and around and around and around in a circle. And in this region, there is magnetism in the middle that is contributed to from all parts of the coil. And because all those parts of the coil are all fairly close, it's a very strong magnetism. So here's the magnetic field inside the coil. B equals mu naught Ni. That actually looks so far fairly similar to the formula we had before. It has a mu naught in it, like before. It has an amount of current in it, like before. Now it has an N. N is just the number of times the current goes around the loop. So you wrap the wire around and around and around. And then on the bottom, it's 2 times R. There's no pi. So in this formula, the other things are exactly what they were before, but that capital N is the number of loops of wire, the little r is the coil radius, and this tells you how strong the magnetic field is inside the coil. So there's a couple of reasons why the magnetism is stronger in this example than it was before. One, we're not dividing by pi. So that makes it 3 times stronger right away. And 2, we can wrap the coil around many, many times. We can have 100 or 1,000 loops of wire in that coil. So that makes the magnetism stronger. Now for a coil, the right-hand rule is a little bit different. Your hand is in the same shape as it was before, but this time it's the current that's going in circles. So your fingers should curl with the current, and then your thumb tells you the magnetic field inside the coil. So our fingers are wrapped in the counterclockwise direction here. Our thumb points out of the page, which means that this coil is filled with dots. Not erasers, dots. Now remember, all magnetism flows in loops. So this coil is basically like a fan blowing magnetic flux out the front. But the magnetic flux has to go out into the room, curl around behind, and then come back in the back. So it's only the direction of the magnetic field inside the coil that we get to show with the right-hand rule. But that gives us a starting point for knowing where the magnetic field is. So sometimes we do calculations with coils. If we do a graph of B versus Z. So if we measured the magnetic field actually in the middle and then above the coil a little bit and above it a little more and above it a little more, the further away we get, the weaker it's going to be. And the graph ends up looking kind of like this. Oops. Like that. So this magnetic field is actually fairly strong inside the coil, but it gets weaker in front of the coil, it's weaker behind the coil. And it's tough to find a place where you have a nice uniform magnetic field. We like to do experiments with uniform fields because that gives us the opportunity to say that the B is the same value everywhere, which makes all the math easier. But this magnetic field is not very uniform. Now, one way to get around this is to add another coil. And if you add another coil, say a little bit in front of the first one, then you'll add another bump. And the overall magnetic field will be the total of the two bumps. And it'll go up, have a little bit of a dip, and then go back down again. And you can make a magnetic field that kind of has a little plateau in the middle. And in the middle of that pair of coils, you'd have a fairly consistent magnetic field. That's what next week's lab is going to use. Two coils that are near each other, that both have the current going in the same direction, so that inside there'll be this region where the magnetic field is fairly uniform, fairly constant, same direction. And inside there, we're going to throw electrons around and watch them fly in circles. I think that's one of the fun labs. Just don't touch the metal parts of the wire next week, because that's the lab where if you touch the wrong wire, it can kill you. We don't want to do that. Yeah. We'll say it in lab also. We'll reiterate that point, because so far we have a pretty good record. Nobody has died. Now there's another type of coil called a solenoid, which kind of takes advantage of the same idea I talked about with two coils. By creating more than one bump, the total of them all forms kind of a plateau. And that is the kind of coil that was in this week's lab. And a solenoid is just a coil where the loops of the coil are in front of each other. So with a regular coil, the wire kind of forms a donut, and you could grab onto it and you'd have 100 loops of wire squished inside your hand. And coil would go around, and you could grab the other side. With a solenoid, the loops go around and around and around and around, and each one is in front of the other, and they form kind of a cylinder. So I like drawing the solenoid because I learned how to draw a solenoid from one of my physics professors many years ago. So first, I like to draw a cardboard tube or a plastic tube around which I'll wrap the wires. And then I've been drawing my current as a blue line. So I'm going to have the current go up the back and down the front, and up the back and down the front. And I'm kind of drawing sine waves, but picking my pen up whenever I'm drawing behind the tube. And then we have to have a battery that is emitting current out the plus end of the battery, as all batteries like to do when you're using them. So this current is going down the front of the solenoid. And each one of these loops of wire can follow the right-hand rule for determining the direction of the magnetic field. So we wrap our fingers around the coil in the direction of the current, and our thumb shows us the direction of the magnetism. So up the back and down the front. And therefore, the magnetism points towards the right inside the coil. And the nice thing about a solenoid is it produces a very uniform magnetic field. Its B is equal to mu naught n I over L. And sometimes different people like to write this formula slightly differently. Sometimes people like to write it as mu naught times a little n times I. And n, bless you, is n over L is called the density of loops of wire, or the density of turns. So that's a nice, straightforward formula to have to deal with. And if we graph this, we get, hopefully, the graph that you saw in lab, B versus Z, where it's fairly flat at first, and then it kind of curves down and flattens out. And this is inside the coil, and this is outside the coil. So basically, the magnetic field inside the coil is fairly uniform, fairly same strength. And once you get outside the coil, it drops down almost to zero pretty quickly. Hopefully your graph from the last part of the lab looks like that. Actually, it's the second to the last part of the lab. All right. Does anybody have any questions? So this gives you a bunch of calculations you can do about magnetic sources. On Monday, we're going to talk about magnetic effects. So we'll talk about the force that a magnet can exert on something, on a wire, on a particle, and then you'll be able to calculate all kinds of cool things about magnetism.